Hello, everyone. Thank you for joining us. It is my greatest pleasure to introduce my colleague, Dr. Oliver Slattery. Oliver is the leader of quantum communications and networking project in NIST Information Technology Lab. The research has significant impact and interested many of us. We are very glad to have Oliver before the holiday. This is a great holiday gift for all of us. Now I will give the floor to Dr. Oliver Slattery. Please go ahead, Oliver.
Thank you, Dr. Chen, and thank you for the introduction, and thank you also to the organizers for the invitation. My talk this afternoon will be an introduction to quantum communications and an overview of the research that we perform in the Quantum Communications and Networking Project here at the National Institute of Standards and Technology, which is actually more commonly known by its acronym NIST. And for the benefit of those of you who are not so familiar with NIST, I would like to just take a few moments to give a short overview. Okay, so NIST was established in 1901. NIST was established in 1901 as National Bureau of Standards, making it one of the oldest physical science laboratories in the country. And the operating budget back in 1901 was $40,000. Today, the operating budget for NIST is over $1 billion, and there are probably over 3,500 employees and as many more associates which are contractors, students, or visiting scientists. And since 1997, NIST has won 5 Nobel Prizes and numerous other national and international awards. So for an organization actually that deals with some of the most complex of science and technology, the NIST mission itself is actually pretty simple. And that is to promote US innovation and competitiveness by advancing measurement science, creating standards, and developing technology in a way that enhances the economic security so as to improve quality of life. NIST has a number of important strategically focused areas, which includes quantum information science, but also a number of other technologies such as cybersecurity. Cybersecurity, artificial intelligence. In fact, all of these areas listed here that can be enhanced by quantum processes. And as part of that quantum information science agenda, NIST was one of the agencies tasked with developing and implementing the National Quantum Initiative Act. And the purpose of the National Quantum Initiative Act is to enhance US leadership in quantum information science and in its technology applications, to accelerate quantum R&D for the economic and national security well-being of the country, and to provide an overarching framework to strengthen and coordinate quantum information science research across the government, across the emerging private sector quantum industry, and academia. So with that overview of NIST, I want to move on to discuss quantum communications and our own research interests and activities. And so here's an outline of the rest of the talk. I'll provide an introductory tutorial to quantum communications, which includes a description of some basic single photon and 2 photon cryptography protocols, as well as a scheme that can be used to teleport quantum information between 2 separated parties. I will then outline the need for what's called a quantum repeater for long distance quantum communications and for quantum networks. And that will serve as a motivation for the particular research my own project team are engaged in. So the goal of communications is to send a message between a point A and a point B, and to do so securely. In traditional analog and digital communications, an eavesdropper can tap into the strong electrical and optical signals and access the message. Now, of course, the content of the message will be encrypted, but if Eve can figure out that encryption, then she can read the message. But quantum communications is fundamentally different. Instead of using strong optical and electrical signals, the ones and zeros are stored on individual particles called qubits. And the most common type of qubit is the polarization state of a single particle of light, which is called a photon. And a key feature of these qubits that is related to some of the fundamental laws of quantum mechanics is that if you try to extract information from them, their state will be changed. And it is by detecting that change that it is possible to detect an eavesdropper. And now when two particles are involved, they can form what's called an entangled pair, meaning that a very strong correlation exists between them, even though they can be physically separated. And we'll see these effects a little bit later on when I go through the tutorial. But for this presentation, the little red dots here represent single photons, and the arrows around them represent well-defined polarizations. When the dot is surrounded by a blurry circle, well, this indicates that the photon is unpolarized. But first, I want to have a quick look at polarization from a more familiar classical perspective. Polarized light, such as from a laptop display, will range from being fully transmitted to fully blocked by a polarizer, depending on the relative angle between the light and the polarizer. And we can note that about half the light is transmitted if the polarizer is aligned diagonally. And an important point here is that once the light passes through the polarizer, it becomes polarized at that angle. We can see this in the final picture here, where an additional polarized slide changes the polarization such that the light can now pass through the polarizer that would otherwise have blocked it. It's interesting, of course, that an additional physical obstacle in the way of the polarized light actually increases its transmission, but that's the nature of polarized light. On the other hand, unpolarized light, such as from an ordinary bulb shining through a piece of paper with an image on it, well, that will be transmitted about half the time through the polarizer, no matter how the polarizer is rotated. Once again, though, once the light does go through the polarizer, it itself becomes polarized at that angle. Okay, so with that bit of background on polarization, we can now move on to describe single photon quantum systems. And for starters, we will need a source of single photons. And these photons can be polarized in either a horizontal or vertical direction in what's called a HV basis, or they can be polarized in a diagonal basis, giving us at least 4 possible qubit states. And for quantum information processing purposes, these states can be assigned either a 1 or a 0. Now, at the other end of the quantum link, we will measure the qubit states with a device called a polarizing beam splitter. And a polarizing beam splitter is similar to a polarizer, except that instead of transmitting and blocking the light, it transmits and reflects the light according to its polarization. So, for example, a vertical photon would be transmitted and a horizontal photon will be reflected. A diagonal photon, though, will be randomly transmitted with equal or reflected with equal probability. And this leads to an obvious application as a quantum random number generator. And indeed, such systems have been developed based on this principle. And as before, the photon will become polarized at the angle of the output photon will become polarized at the angle of the polarizing beam splitter. And this is a key feature for quantum cryptography, as we'll see next. Now, if we rotate the polarizing beam splitter diagonally, then it will be the diagonal photons that will be predictably transmitted or reflected. And it will be the horizontal and vertical photons that will be randomly transmitted or reflected. So now we can walk through a basic 1 qubit QKD protocol. And QKD stands for quantum key distribution. And the idea is that Alice and Bob can create a secret shared key. First of all, Alice will prepare a photon in one of the 4 polarizations and send it to Bob. And Bob will measure that photon in a random measurement basis. If he chooses to measure the photon in the same basis that it was corrected, as he does here, then he will always get the correct result. If he does not measure in the correct basis, however, he'll get a random result. And so after he makes the measurement, Alice will tell Bob the basis she used to create the photon, not the value she assigned to it. And Bob will then know if he got a correct result or a random result. Note that they never share publicly what the result was. They only keep the results, and they also only keep the results where the correct measurement was made. And in this way, they can create a secret shared key. So what happens if an eavesdropper tries to intercept the quantum state? And just like Bob, she will have to guess a measurement basis. If she guesses wrongly, which she will do about 50% of the time, then the measurement will change the state of that photon. Now Bob will get a random result, even if he and Alice use the same basis to create and measure the photon. So as part of the protocol, Alice and Bob will compare a sample of these results, and they will realize that there's an error. And this will indicate to them that there was an eavesdropper listening in. And that's the basic principle of quantum key distribution, although there's a lot more to it in practice, including error correction, qubit reconciliation, and so on. But that's the basic idea. Okay, so now we can move on to 2-qubit entangled quantum systems. Again, we'll need a source that can generate entangled photon pairs. And entangled photon pairs are unpolarized. So unlike the polarized photon, by measuring either one of these entangled photons, we get a random result, no matter how the polarizing beam splitter is arbitrarily rotated. However, once we have measured one of the photons in the entangled pair, what about the other photon that has been physically separated? So the second measurement will no longer give a random result. In fact, it will give a perfectly correlated result. If the first photon is randomly transmitted through some arbitrarily rotated polarizing beam splitter, then the second photon will always, 100% of the time, be also transmitted through its polarizing beam splitter when it was measured at the same arbitrary angle and only at that angle. It's as though that it is though the measurement on one qubit causes a second physically separated qubit to orient itself so as to satisfy that correlation. And the question then becomes, how did that second photon know which arbitrary angle was used to measure the first photon, and how did it know the result? Einstein, of course, famously has referred to this phenomenon as spooky action at a distance. And these entangled pairs, they can be used for various protocols, including quantum cryptography and quantum teleportation. Now, in cryptography, Alice and Bob would each receive one of the photons from the pair from the entangled pair, and they would both choose a random basis to make their measurement. If they choose the same basis, they will get perfectly correlated results. But if they choose different bases, their results will be random. So they will only keep those results, those bits that they used when they measured using the same basis to generate their secret key. Now we have to consider what happens if an eavesdropper tries to intercept one of these photons. The entanglement and correlation will be destroyed, and now Alice and Bob will get uncorrelated results even if they use the same basis. And this again will indicate to them that an eavesdropper is present, and so they won't be able to create a shared key in those conditions. Now, so up to now, we've been making measurements using an optical device called a polarizing beam splitter. But there is a different type of measurement that can be used, and it's called a Bell state measurement that is based on interfering photons. Now, while this can be very, very challenging in practice, if certain conditions are met, then two independent photons can be interfered so as to become entangled. Now, if one of those interfering photons is itself originally from an entangled pair, then the interference process not only affects that photon, but it also affects its corresponding photon. The entanglement is effectively swapped from the original pair to the interfering pair as part, and that is a key part of the teleportation process. In this case, Alice has a qubit that can be known or unknown to her that she wishes to teleport to Bob. So she will interfere her photon with one of the photons from the entangled pair. The second entangled photon is sent to Bob. When the interference occurs at Alice's measurement, Bob's photon will be affected even though it is physically separated, and the random result that Alice gets with her interference measurement can be used to inform Bob what he needs to do to recreate that teleported qubit state from his photon. But sending single particle photons over very long distance is hard due to losses or decoherence in optical fibers, for example. And because the quantum states are protected by some of the fundamental laws of quantum mechanics, the same laws that allow us to detect the eavesdropper, they can't be copied or they can't be amplified as can be done with classical signals. So to get over this problem, there's a device that can be built, and it's called a quantum repeater that uses entanglement swapping to share entanglement between physically separated links. Ultimately, by implementing several of these quantum repeater links, the distance between the two parties can be much greater than what would be possible over a direct link. And in addition to long distance entanglement distribution, quantum repeaters can be used to establish a link for entanglement routing around a quantum network. One could imagine many of these quantum repeater nodes being constantly creating new links that can then be called upon by a network manager to optimally entangle any 2 points in a quantum network. At the same time, because what these devices essentially do is entangle separated quantum systems, they may also be used to connect different types of quantum computing technologies and form quantum computing networks in order to scale up the quantum computing power. So now, because these quantum repeater protocols use 2-photon interference at a Bell state measurement, the interfering photons require very tight timing, frequency, and directional tolerances. This actually is one of the reasons that makes the Bell state measurement very, very hard to implement. So in order to prepare for a Bell state measurement, the quantum states can be captured and stored in what's called a quantum memory just before the Bell state measurement, and then released on demand in such a way that it can greatly increase the success probability of the Bell state measurement, interference. And so in our project, we developed some of the key components that are needed for such a system, including the single photon sources, interfaces, interference measurements, quantum memories, and single photon detectors, and so on. For quantum memory, we use a process called electromagnetically induced transparency, or just EIT. And so EIT is a technique that can be used for capturing single photon states onto the atomic ensemble based quantum memories, and after a period of storage, releasing the quantum state again as a photon on demand. And since it's on demand, the tight timing synchronizations required for the Bell state measurement can be optimized, even if these photons were generated originally in independent sources at different times. And because each state is stored in very precise frequency transitions of the quantum memory's atomic structure, the emitted photons from 2 quantum memories of the same type are also very well matched in frequency. But this type of quantum memory scheme uses a very strong control light to effectively turn on and turn off the transparency in order to capture and release the photons. And this actually strong light is actually collinear and almost at the same frequency as the single photon signal, which makes it very challenging to isolate the single photon from the strong control light. And so to address this, we've implemented some noise reduction techniques in our quantum memory scheme, which includes a combination of atomic absorption filters, customized echelons, polarizing beam splitters, and other techniques to eliminate the strong control beam by over 120 dB, which effectively is below the single photon level, while at the same time transmitting the actual single photon signal at 50%. Now, we've implemented EIT at room temperature, in which photons from a weak laser are captured and stored and released after various times on demand from the quantum memory. And we're also working on implementing low temperature EIT using a magneto-optical trap, which will greatly reduce the noise in that system. Now, just as I mentioned, EIT quantum memory uses very precise narrowband atomic transitions to store their quantum states. But the primary process that we use to generate single photon pairs is a process called spontaneous parametric down conversion, or just SPDC, in nonlinear crystals. Now, this is naturally a very broadband process, orders of magnitude too broad, in fact, to have any meaningful coupling into the narrow selection bandwidths of the quantum memory. And so to address this issue, we put our nonlinear crystal sources into resonating cavities whose modes can be locked and stabilized to the very precise quantum memory frequencies. The cavity effectively squeezes the generated pairs into narrow, brighter modes of the cavity. And we're currently working on to couple these photons into our EIT-based quantum memory, especially once we have implemented the low temperature scheme. Of course, in any quantum communications or a quantum networking system, there will be a need for interfaces. Different processes such as qubit generation, transmission, storage, computation, detection, they're all implemented using processes that are often frequency specific. In a network of these systems, then, we'll have to be able to convert the quantum state while preserving the fragile quantum characteristics from one frequency to another. And we're working on various frequency conversion schemes to interface between telecom frequencies, various quantum memory and computing frequencies, and to and from different qubit generation and detection technologies. And we've actually been early developers of quantum frequency conversion, or QFC schemes. As an example of that, we use our own quantum frequency conversion to convert single photon light at telecom wavelengths, which are optimal for sending light over fiber, to visible wavelengths, which are optimal for detection at room temperature using off-the-shelf silicon detectors. And we achieved an overall detection efficiency of 35%, which is actually quite high for these elusive photons, and doing it at room temperature to control the noise. But for most quantum communications and quantum networking applications, the highest possible quantum detection efficiencies are really essential. And it's for this reason we've been expanding our group's capabilities recently to include superconducting single photon detectors, which can achieve detection efficiencies above 90%, 95%, even with very low false, or what we call dark counts, and that's due to their low temperature operation. So future quantum networks, of course, will be complex and heterogeneous in terms of the physical components that make up the network, such as fibers, sources, detectors, various types of interfaces, even the physical connectors used. Heterogeneous in terms of the protocols, heterogeneous in terms of the applications, and so on. And they will also be ever changing as the components or as links within the network are being activated and deactivated during the operation. So to monitor and optimize the networks, then, we will really need to understand both the individual components as baseline predictable parameters, but also understand the network, how the network is operating more globally. Now, NIST is not new to building quantum network testbeds. Many years ago, our own group implemented a QKD network that created an actively shared keys on a small multi-node network testbed. A surveillance video, rather, that was QKD encrypted was sent through the internet from 2 remote locations to a central location. And the quantum keys were then created over local quantum channels for decryption of the surveillance video at that central location. Currently, our colleagues at NIST are implementing a high-speed classical network testbed on the NIST campus called the Platform for Network Innovation, which will be used to develop novel classical network protocols to, for example, find optimal routing streams within a network. And we've been working with them to extend this testbed to have dedicated quantum channels. And we'll be using this quantum network testbed on the campus to develop our own quantum network metrology toolboxes and quantum network control manager. And we'll also populate the network testbed with various NIST developed and commercial quantum components for characterization and testing. So one could imagine the need to implement protocols for real-time configuration of a quantum network link, should that link be noisy, for example, or should that eavesdropper be detected on the link. And we're also working with other DC area federal agencies to create a regional quantum network testbed called the DC QNet. And we hope to be implementing that network testbed over the next couple of years. So with that, I would like to say thank you for your attention. And this is my team. I would like to acknowledge them and their great work over the last many years. So thank you for your attention. Our website is listed on the bottom left-hand side of the slide. Thank you.
Thank you, Oliver. I saw a question in the chat. Can you read it, or you want me to?
Let's see. Let me see if I can get at that. Bear with me just a sec. So the question is about what's been done to protect cryptocurrencies. So, you know, I guess the way I would like to answer that is to bring attention to another type of quantum safe communication, or communications that is protected from it is what's called quantum safe cryptography. This is actually a classical cryptographic system that Dr. Shen is very, very familiar with. And that will probably be more useful in the near term for ensuring all sorts of classical attacks on the cryptographic system, on the cryptocurrency systems. It's interesting to note that Quantum 2.0, which is kind of the application side of quantum technology, began with a proposal for quantum money back in the 70s. So it's interesting that that's coming around again. That now quantum security may be needed for money as it develops in cryptocurrencies.
Maybe
go ahead.
Yeah, maybe I can add a little bit, because for the blockchain or cryptocurrency, you use hash function and digital signatures. Not really use encryption. So from that point of view, it still uses the classical cryptography, I think. That is not use QKD.
At this stage, yes. And of course, it's true also to say that even when quantum communications and quantum cryptography gets established, it will be as a complement to classical systems, not to necessarily replace them. So there's another question here from someone. It says, if I understand correctly, if you will be able to change the frequency and preserve the quantum information, it would be essential for a quantum router, i.e. a repeater plus a wavelength switch. So I think that's correct. You know, a quantum router, a quantum switch, so there's an optical switch, and then there's switches that are based on quantum processes. A quantum repeater definitely is a wholly quantum process, and so if a quantum router requires a preservation of the entanglement, like you say in the question, then yes, it will. It sounds like that's what a quantum router is. Yeah, so I think that's true.
So, any other questions? If no question, let's all thank Dr. Slattery for the great talk, and everybody have a great holiday season.
Thank you, Lily. Thank you, Oliver. Everyone have a great holiday.
Thank you very much.
Thank you very much, Oliver.
Thank you very much,
everybody.
Bye-bye.
Bye-bye.